welcome on stage Maximilian Eberle, Vehicle Dynamics Simulation Engineer, and Alessandro Porro, Performance Engineer, both from MERCEDES-AMG. In this presentation, they'll explore the evolution of digital control systems and tire models, reshaping the landscape of vehicle dynamics. Discover how AMG leverages VI-CarRealTime models and the FMK-Tool to bridge hardware and software simulations, revolutionizing testing and implementation processes.
So, welcome to our presentation of the enhancement of digital control systems and tire model for automotive development. My name is Maximilian Eberle. I'm a simulation engineer in vehicle dynamics at MERCEDES-AMG, and this is my colleague.
I'd also like to welcome everyone here today. My name is Alessandro Porro, and I'm a performance engineer at MERCEDES-AMG.
So, before we start, I also want to thank Rebecca Lirsch and Bidlingmaier, the co-authors of our presentation. So, I would say, let's start. Our motivation at MERCEDES-AMG is to develop the best possible digital prototype, not only to reach a high level of maturity in the early hardware design, but also to take these models for the early control system and software development. To address the conflict between the short time in development and the increasing complexity in signals, in models, in cars, and of course, to trust our simulation results, we are forced to use modern and sophisticated methods to deal with these problems and to reach reliability and reproducibility. This method also enables us to implement the new AMG tire model. Our goal is clear. We want to make the step into the virtual validation of control systems in vehicle dynamics. So, I would say, let's start and let's go. So, this is our action plan for today. You can see it here. With the first 3 points, the AMG Virtual Garage, the implementation of the active systems, and the dynamic model configuration, I want to take you to a journey of methods and handling of our vehicle models. On the fourth point, Alessandro will talk about the AMG, the advanced AMG tire model. And on the last point, I will summarize all together up in an automatic testing environment, of course, for offline and online simulation. No wasting time, let's go. Before I start with the AMG Virtual Garage, I want to explain how we define or describe our vehicle models. So we have here a vehicle model configuration, and we can split up this vehicle model configuration in mainly 3 parts. So first of all, we always have a VI-CRT base model, our baseline for all of it. On the second part, we are used to implement right there our active systems, and one of the most important part, our AMG components. But now, first of all, we are dealing with the VI-CRT base model. Before I start, we have to say that this method was created due to the growth of the organization and the increasing number of models and cars we have in our organization. So once an MBS engineer exports a model from Adams to VI-CarRealTime, he or she usually has his or her model locally. But to increase the accessibility and exchangeability of our models, we said, okay, why not to have a virtual garage where we can put all our models in. And this is called the AMG Virtual Garage. So it is cloud-based here in Bitbucket, and we can take our car, and when we take our car model and or our system file, our subsystem file, and our third level file, we usually split it up into our BOM, our bill of materials. And we put these files and put it into our goods cupboard. Like you can see, for example, the tires and the chassis. And when we pull a car out of our virtual garage, we only have to take the system file and all the subsystem files and the third level files which are linked to our system file come with us. So to summarize all the advantages up, we can say that we have now a central location for all our models. We have the accessibility for all our vehicle dynamics engineers. We can document our models well, so versionized revision systems, subsystems, and third level files. And of course, we can make the usage of the concept of blocking, because when two cars use the same spring file, for example, I only have to update once the spring file, and when I pull a car out of my garage, it always gets the latest update of it. And of course, we implement the possibility to export our models in an open or an obfuscated mode for internal or external usage. So, next step to level up our digital models is the implementation of our active systems. So when I talk about active systems, I usually talk not about the Simulink models we have. I talk about these sorts of models, like target link models, amnesty models, C-code, or fixed database sets I want directly linked to my VI-CRT model. When I have an update in the structure of these models or in the parameter set, I do not want to have to do and to link the models by manual. I have there an automated CI/CD pipeline, and this automated CI/CD pipeline allows us to build up FMUs. And of course, they are cloud-based too, here in the Artifactory and with the node for Linux and for Windows. So I want to use my FMUs in the Windows platform and on the Linux platform. And it should be the same. And of course, we have here a logical structure to put it into our Artifactory. And to summarize here up, I want to say that this is triggered in an automated way. So one click I do not have to do one click, so everything automated. I can supply fixed software releases, and I can receive fixed software releases and put it in my folder structure here too. I can build up platform-independent FMUs, so by usage in Sim Workbench online or only in VI-CarRealTime offline. And of course, I make the usage of the easy connection of VI-CarRealTime by the FME master and by Sim Workbench by pathing it into the real-time database. Now, the third one, the dynamic model configuration. Before I go into the method, I want to explain the motivation behind it. By using the dynamic model configuration, I use the benefit of the co-simulation in MATLAB Simulink together with VI-CarRealTime or the compiled version then to Sim Workbench. So with my AMG components, that's a database we build up in Bitbucket, well documented too, I can reach a higher and more detailed simulation accuracy in all of my models. I can directly integrate controllers, modules, principal controllers, and so on. And of course, this is one main part where I can implement my control systems. And I can do my developments on signal level. That's a big point here. So, and these models in our database are Simulink models. So once I get a Simulink model, I add it into a Simulink library, and I build up the signal list. In the signal list, the in and the outputs are fixed, and of course, information about signal type, signal dimension, and signal units. Because later I need some calculations when I put all the modules together, and that's the reason why these informations are here too. And of course, at least one parameter set. So, and this is our dynamic model configuration. I can select a target, so I can select the online or the offline version. Online is the simulator, offline my VI-CRT co-simulation. I can select the VI-CRT base model, and of course I can make the usage of all my libraries and the databases I have in my Bitbucket here and build up a compilable Simulink model. I can use it offline and make some investigations in the mill or SIL, or I can use it in the online version and going to the hill or the driving simulator with it. And the dynamic model configuration was also the beginning of the AMG tire model. And now I will give the stage to my colleague Alessandro, and he will take you to a journey through the AMG tire model.
Thank you very much, Maximilian. So, well, let's talk about the tire model and how we implement it into the dynamic model configuration and what we did during the development. But first, we have to define a starting line, where to start in such a development. Well, we have to define the requirements, what we need from a tire model in order to do control system development. So the model should be real-time capable. So we want to use the tire model on the driving simulator. We also want to be able to start from zero velocity conditions. So the model should be able to handle standstill conditions. We also want to be able to make decisions in an early development stage. But what does it mean? Well, not only that the results of the model should be trustworthy and realistic, but also that we should be able to get the parameters for such a model in an early development stage and not wait too long till we have also a real prototype of the tire. And then, furthermore, the model should be able to handle different road conditions, so different friction coefficients, mu split, mu jump, and so on. And last, the dynamic response of such a tire model should be realistic and should have a proper response to slip control intervention. So the first 3 points will be a little bit our boundary conditions and also the reason why we decided, okay, let's start with the magic formula-based model. And the last 2 points will be a little bit what I'm going to show you today and the goals for improvement. So first, we can take a quick trip to Sweden and go with different road conditions. So here we can see 2 different curves of a tire. The blue one is with high mu, and the orange one is low mu. So this is the typical scaling of a magic formula-based model. We have a linear scaling. That means that we are just scaling down the force of the curve, multiplying with the friction coefficient. However, this is not realistic according to our literature research. And we had to confirm this hypothesis, and we were able to, working with a tire manufacturer to get a second parameter set for the same friction coefficient. And this is the yellow line. And we can see that the maximum force is similar. However, the shape of the curve is quite different. But this is also not a feasible solution because for, 10 different friction coefficients, we need 10 different parameter sets. And if we have a mu jump situation on driver simulation, we have to, we have to stop the driver, say, hey, hold on, we have to load the parameters files. Okay, now you can go. This is not really real time, and we want it real time. So we found also a model that is able to do this scaling online. And we can see here the green line. We have a good accuracy in the 2 main ranges, which are the linear range and where we have almost 100% slip. And those 2 ranges are important when we are simulating with or without a slip control system. Okay, good. But we also wanted to improve the dynamic response because this curve is only valid for quasi-static situations. And again, we need the starting point, and the starting point is VI tire. Why VI tire? Well, the model is a good, stable model, reliable, has a lot of advantages, but we found also 2 main limitations, that we are limited to only 2 different versions of magic formula parameter set, and we can only use the linear dynamic for the transient behavior. So what we did, we built from there up, and we implemented the belt dynamics for the rotations around the y-axis. We also implemented different transient behavior models, so linear, nonlinear. We implemented the latest formulation of the magic formula equations, as well as the mentioned before, the scaling, the improved scaling for the road friction behavior. So what we did then, again, dynamic model configuration, we need the Simulink models. We build the model in Simulink so that we can use it in the dynamic model configuration. We can run co-simulations with VI-CarRealTime. And now we have also to check that the model actually achieved those improvements that we wanted to achieve. So what we did is, on a hill system, we did an ABS maneuver with VI tire. And here we see the results. We see that we have 3 major problems. A lot of vibrations when the wheel recovers from great slip conditions. We also see that we cannot recover from a slip condition at low speeds, so we are locking the wheels and not able to control the slip anymore. And we have also big peaks in the longitudinal slip in positive direction, which means, yeah, that's not really realistic because we are braking. So same maneuver with the same system, same control system with the AMG tire model. And we can see that we were able to effectively improve the model. We don't see so many vibrations when the wheel recovers from a great slip condition. We can still control the slip till 0 velocity. And we can also see that the peak, we still have some peaks in positive direction, but are way lower and only happening at low velocities. So then we were actually able to cross the finish line and to reach all the goals we wanted to achieve. And now we have a model that we can use for testing, and I'll give the word back, or the stage back, to my colleague, Maximilian. So please, go on.
Yeah, thank you, Alessandro, for my good tire model right now. So I have now an advanced vehicle model with my VI-CarRealTime base model, the active system and the AMG components with an AMG component, the AMG tire model. And I have the optimization or optimal interfaces to link my control system here. So as in software, so as an active system or as a model in the loop. But when we want to analyze results, we have to generate results. And how we generate results? Yeah, we have our vehicle model, and we build up a tool for defining driving maneuvers. So it's called our driving maneuver catalog. And we can here define longitudinal, lateral, or the combination of both, even vertical maneuvers, and yeah, generate a great testing plan here. And now I want to go with this setup into the simulation and into the automated simulation. And we made the offline simulation here, because when I have the vehicle model and my control system only in the software version, I have to connect it here. I take my testing plan and the driving maneuvers, and I can run the automation in MATLAB Simulink. And when we have our software as an hardware available, I also can do this hardware in the loop. So by connecting the hardware with some workbench and VI Drive Sim, and to run the automation online. So yeah, we need here a little bit more effort, because we have to change the environment from Windows to Linux, but it's also possible. So a sneak preview here for our testing automation. So now I would say our mission here is completed, and I want to thank you for your attention, and please ask your questions. You're welcome. Thank you.
Thank you.